CS225 final project, Dijkstra's road trip. Our goals for this project was to create the shortest path between points of interest in California. By shortest path, we define it as a geographical distance between 2 points instead of time of travel. Our idea was to create a memorable road trip in California. These points of interest was to be inputted into an algorithm that will be used to create the shortest route between them. Also, the way these points of interest will be hit would be determined by our shortest path algorithm. The original plan was to create a list of 20 points of interest and create paths between up to 5 of these points of interest. However, we couldn't get it to work. And even though we were able to implement all of our proposed ideas, we couldn't fulfill some of the goals because of the large size of our data set. And even though our algorithms worked as well, our runtime became extremely large as a result. During our development stage, we acquired our data from Harvard's Dataverse of US Street Network Node Edge List. We chose California as our state only because there were so many points of interest that we could use in our program. And with this, we decided to use BFS as a traversal, and for our shortest path algorithm, we used Dijkstra's algorithm with heap. We chose BFS over DFS only because it would be more efficient, and we chose Dijkstra's because it was an effective path finding algorithm.
So we chose California because of the plethora of points of interest that we liked, but it also came with a very large data set. And so when we went to implement and run Dijkstra's algorithm, the runtime became a little too large for us to actually just have the algorithm finished. And then there was also a little bit of pixel misalignment between nodes and edges when we were creating the visualization. But besides that, when we were testing the code, we wrote 7 test cases that confirm that Dijkstra's and BFS work on a smaller data set and that they work according to their runtime.
As far as our BFS traversal goes, it was very successful and traverses every node in the expected amount of time. On the right, you can see the 2 test cases we wrote to check over the unvisited nodes prior to the traversal. And you can also see that after the traversal, we visit all 1.2 million plus nodes. So it works as expected and goes through all the nodes we have in our data set. The heap has an efficiency of ON and somewhat limits the success of Dijkstra's algorithm on such a large data set due to the fact that it has to essentially heapify every time a node is inserted and added into the list. So essentially, our runtime gets worse the more nodes we add.
So for Dijkstra's algorithm, it was definitely significantly handicapped by the runtime of make heap. And that's unfortunate, but it's not really anything we can do because we did use an efficient implementation of Dijkstra's algorithm. It's just that because we have millions of nodes, it's not going to run in a reasonable amount of time. It fails to function at full scale, but it does work well in small sets. We even ran it on sets like the state of Rhode Island, Champaign-Urbana, even worked on Wyoming, but not California, because California has so many roads and so many large population centers with lots of roads and intersections in them. So what our algorithm actually did was return a vector of consecutive nodes, and then we could use those nodes for our visualization algorithm. And the test cases we ran for Dijkstra's algorithm included some to make sure that if the nodes that we selected weren't connected, then Dijkstra's is going to output like a standard output saying that it's impossible to connect them. And then we did a few test cases where there's multiple possible paths and made sure that it selected the shortest possible path. So the visualization we made basically takes the paths, or the idea was to take the path of nodes from Dijkstra's algorithm and draw them on the map of California. But unfortunately, Dijkstra's algorithm didn't run, so we didn't have a path to draw on California. So instead, what you see on the right here is just all of the nodes in blue. Each one is 1 pixel, and then there's some orange squares, which are the points of interest that we chose that you could make paths between. And on the bottom left, I have a small like sample path between nodes. So I basically just took random nodes and made a path between them just to show you what our path would look like. And it didn't work out perfectly. There are some gaps in our path that we couldn't quite fix, but it gives you a good idea of where the path is. And if it was on the whole state of California, the path would give you a good idea of where you would have to go. The shortest path really only works on smaller sets due to the inefficiencies we talked about earlier. So in the future, we'd have to choose a smaller area to get the visualization to work well with Dijkstra's.
So over these past couple weeks, we've been trying to answer the leading question: what is the shortest path between pre-selected points of interest according to Dijkstra's algorithm? And so we wanted to output a path on a visual on an image that could let the user visualize the route that they chose, similar to how Google Maps does. And so we had a very large data set of over 1 million nodes and 3 million edges. And so in the future, we would want to make a visualization that we want our Dijkstra's algorithm to work so that we could show the user their route a way that Google Maps does, and do it in a way that is efficient enough and practical for actual use.
So as far as the things that went wrong, we kind of brushed on them earlier, but Dijkstra's algorithm is limited in its usefulness at scale with the way that we were implementing it, due to the fact that, as mentioned before with the heap, since Dijkstra's relies on the heap to function, the increase in efficiency of Dijkstra with the addition of new nodes to the heap makes it realistically really unusable for the purposes that we have outlined. And we also did not have roads to visualize due to some errors that we ran into towards the end. But with that being said, the heap implementation that we did have is as good as heap can get, but it's still not great. And in the future, if we had more time, or if we were to do this again, we would implement a different way of traversing and finding the shortest path, and we could look into the way a mapping program like Google Maps does it. We could also look to implement our current solution, but on a smaller data set. That way, even though the runtime would be large, it wouldn't necessarily impact the overall efficiency of it at scale. So as far as the individual insights goes, I think personally, this is my first time working in a group with multiple people writing multiple methods. So there was some difficulty trying to get different classes, different methods that people wrote to work together, just because everyone kind of thinks differently in the way that they write code, and everyone has their kind of approach. So I think we would have benefited from having one person plan out code interactions ahead of time, something like a Doxygen. And then that way, each person that was writing the method or the class knew exactly what the output and the input of their method was, and we would have a better time debugging different method incompatibilities or getting different methods to work together better.
So yeah, like we said earlier, if we were to do this project again, we'd probably choose a smaller data set, but even more so, it would be good to understand the requirements of the project before committing to them. We didn't really anticipate having such a big data set would affect the successfulness of our code as much as it did. So yeah, create a Doxygen would help with planning and really going through the requirements and knowing that, hey, is this even this is an idea, maybe we can implement it, but can we implement it well? That's something to think about in the future.
And even though in the future we do want to use or plan to use a smaller data set to complete this, we would also want to see how we can actually adjust our program and our algorithms to actually see if we can make larger data sets work effectively, such as using more like a couple of states and maybe even nationwide data sets.
Yeah, so as we've said 100 times at this point, Dijkstra's was never really going to work on our data set because of the size, but I thought it was interesting to like look into a little bit how Google Maps does this, because they have a very different way of doing it from what I could find online that makes it possible to find those maps like almost instantly. Like it takes a second or two on your phone to calculate a route. And that's not what we were seeing with our implementation. And also there's a lot of working with Git in a group was kind of hard and a good learning experience that I think we all went through. Thank you.
Thank you for listening to our presentation.